Today we start our discussion on machine learning, which, as you know, is one of the most formidable topics today in artificial intelligence. And the ability to learn is one of the most core artifacts of intelligence. And machine learning is about making a machine able to learn things through experience and try to mimic the human behavior through that learning. So, to start with, let's look at the taxonomy of machine learning, and let us look at the different branches that we have in machine learning. So, as I mentioned in the introductory lecture in AI, machine learning today has many different branches. So, broadly we have, in terms of techniques, we have supervised learning, we have semi-supervised learning or completely unsupervised learning. We also have methods like clustering, like regression, reinforcement learning, classification, etc., etc. So broadly, if we compare the way that traditional programming solves a problem vis-a-vis how machine learning solves a problem, then that is shown here, that in the traditional programming you have data as the input, which is the inputs that you give to the program, and you have the program, and you execute the program with the inputs and you get the outputs. Whereas in machine learning we have data and we have legacy data which shows the behavior of the system that we are trying to learn. So you have the output data already from a real system, and machine learning tries to learn the program or the function which can then explain the output for the given input. So it's really the idea is to learn the function that fits the output data with respect to the input data, and our objective is to learn that function. For this lecture, most of the material that I am going to discuss is from an introductory chapter in this book, where the chapter on machine learning fundamentals covers mostly what of the things that I am going to discuss today in this lecture. So let us start by looking at the generic question of what is machine learning, and let me bring it to a full screen. Right. So in Michel's iconic book in 1997, he referred to machine learning by the following definition. It says a computer program is said to learn from experience E with respect to some class of tasks T and some performance measure P if its performance at tasks in T as measured by the performance measure P improves with experience. So as you can see here, there are a few important terms which we need to understand and imbibe in our discussion in this chapter. So firstly, we have the experience E, which is indicated here, the experience E, and we are to learn this for some class, some category of functions or category of tasks T, and the quality of machine learning will be evaluated using some performance measure P, and if its performance on the tasks in T as we measure by P, if it improves with experience E, that is, when we present with more and more experience, if it starts improving with that, then we say that the program is learning. So let's look at some examples of the task T. I will first cover some of the examples of the task T, then we will discuss what we mean by the performance measure P and what we mean by the experience E. So these are the three important terms that we need to understand before diving into any of the techniques of machine learning. The task T in machine learning can be quite varied. So it basically embodies what we want to learn. So for example, in the standard classification task, we are trying to learn a function which goes from r to the power n to 1 to k. Now what does that mean? It means that I have n dimensional space and I want to classify these points in the n dimensional space, and I have these different classes that I am defining here. There are k such classes, and every point it's mapping to a class. So maybe this is class 1, so all these points here in this region, they map to class 1. Then if this is class 2, then all these points map to class 2. So those are the class numbers are here, and this is the n dimensional space from where every point is getting mapped to one of these classes. So that is the classification problem. Then I look at classification but with missing inputs. Maybe some of the inputs are not there and I still want to do the classification. Another important class of tasks which people attempt with machine learning is called regression. Regression is the standard requirement to learn a function which maps every point in an n-dimensional space to some value, maybe in general a real value. For example, given a set of parameters, can I predict the temperature of the next day? Or can I predict, for example, how much of solar irradiance will be there in the next 1 hour, so that I can plan the amount of energy that is going to come out of my solar farm in the next hour or so. I can predict also things like stock market. Many different variables are there, and based on that I want to predict the value of a stock, or I want to predict the value of the Sensex, for example, and so on and so forth. Transcription is another important machine learning task where we want to learn speech to text or image to text conversion. There are literally many hundreds of algorithms which have been developed in the past couple of decades which do transcription with various levels of accuracy. Now in most of the cell phones and in laptops you will have apps which can translate text, speech to text, or it can translate image to text. So you have things like Cortana, for example, where you can read out your commands, and even Google Assistant can read out your speech and convert it to text. Similarly for images. Machine translation is another interesting area of machine learning where we learn to translate English sentences to another language like German or Bengali to English, and so on and so forth. There are many cases where the output of a machine learning can be a structured artifact. For example, I have an aerially captured map or maybe a satellite image, and I want to learn to mark out certain types of things like, for example, roads, rivers, or anything of that type. So then that is, the machine learning is also used to a large extent for these kind of problems. Anomaly detection is a very interesting area. Basically it means that you suddenly discover that the output is coming to be something in the data. It's coming to be something which does not fit the normal distribution that you have learned. So for example, if you learn that a particular person on an average gives a tip of let's say 100 rupees in a restaurant which he visits maybe once or twice in a month, and then suddenly you find on one day that in his credit card there is a tips of maybe 500 rupees in the same restaurant. So then that is an anomaly, and you start wondering as a banker that I hope it's the same person using the card, or has this card been stolen and somebody else is using it, etc. So anomaly detection is something that is a fairly regular task which appears in many domains, and there are many different algorithms for addressing anomaly detection. Denoising is also an interesting machine learning task where you have a lot of data and you want to find out the noises and eliminate them. As you can imagine, it's somewhat related to the anomaly detection problem, because anomaly can sometimes be due to noise, and you may actually want to filter out those noises and get a set of data which is free from those noises. We may at some time also want to estimate a probability density, for example. Instead of learning as in regression, we learn a function from r to the power n to r. We may want to learn a probability of this mapping as well. So then that would be something like a probability density function, and you may map from r to the power n to some value between 0 and 1. Now let's look at the second thing, the performance measure. Suppose we have a machine learning program which has been given a certain type of task, for example regression, and now we want to estimate how well it does. So that is a performance measure. So for tasks like transcription and classification, we often measure the accuracy of the model. So for example, if you want to make a machine learning program, you train it to learn how to recognize, let's say, horses, then the accuracy is measured in terms of the proportion of examples for which the model produces the correct output. For example, the set of images where it recognizes a horse correctly, and the error rate is the proportion of examples for which the model produces incorrect output. So that may be both on the positive side as well as the negative side. For example, it may not recognize a horse to be a horse, or it can recognize something else, maybe an elephant to be a horse. So these are all errors, and the error rate is the proportion of examples for which it misclassifies. Then we have the data. In the data we have the training set and the test set. So in a machine learning algorithm, as we shall see in the next few lectures, we start the machine learning by training it over a subset of the data which is called the training set. So we use that data to train the model, and then we must make sure, or we must assess how well the training went. So at the end of the training, we apply the model on the test data, on the test set, and we evaluate the performance of the algorithm of the model on the test set, and there we see whether what is the accuracy and what is the error rate to determine how well it has learned. To give you another example of what we mean by this, let me also take an example from the regression area. So just give me a moment. Right. So wait, just let me bring this up a little bit. So let's take the example of regression, where let's say that I am trying to learn a function. So I am given on this side I have the x-axis, and I have on this side I have y, which is the function of x, and I am trying to learn f. So let's say that I am looking at linear regression. So I am given a set of data points, obviously. So let me choose a different color. Okay, so I have, let's say this is a data point, 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 etc. Now what I do is I try to find out a function, maybe a linear function or maybe an affine function, which fits this data. So maybe a line like this. Now what is my error? So my error here is the differences here. Like this is the error of this point. For this point I have this as the error. For this point I have this as the error. For this point I have this as the error. For this point I have this as the error, and so on and so forth. There may be other points, and I can sum up the errors, or some of the squares of the errors, if you please, and that gives me an estimate of how well this function, the green line, fits those points. So what we do is that we don't expose the model at the beginning to the entire data set. So what we do is we keep maybe, let's say, 80% for the training, and maybe keep the remaining 20% for evaluating how well it has learned. So maybe after I have learned this function, then I look at the other data points, maybe the data points which are in the test set. So maybe this is that data, some of these data are there, right? And then I evaluate the performance on those data, right? Now there are different kinds of problems that we have to deal with. For example, that the performance measure is, defining the performance measure is not always very straightforward. For example, when we perform a regression task, there are two types of ways that we could potentially define the performance. For example, one of them is that if it frequently makes some medium-sized mistakes, and the other is that if it rarely makes a very large mistake. Now let us see from a variant of this example. Let me clear this up and then let me get a new or let's see. Let me start afresh with a new set of axes. This is my and I have, let us say here, I have a set of points here, 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 maybe here, okay, maybe one here, and maybe one here, okay. Now if I am interested in, let's say, allowing many number of small errors, then I can probably use a function like this. Now there are many number of small errors, and there is one large error for this one. For this one there is a very large error. The other is that I could potentially say that I want to minimize my maximum error. So then I might go for something like this. Then the maximum error is, I think, either this or this, which is much lesser than the maximum error in the red one. So I can potentially define my performance measure in many different ways, and depending on that, again my algorithm has to be appropriately designed. The next thing that we need to look at is the experience E. So to do that, what do we understand by experience? So just let me flip this around a bit, get this thing back into full screen. There. And get my pen. So for the experience, that is the data that I am getting in the data set, there are broadly two types of learning algorithms, namely unsupervised learning algorithms and supervised learning algorithms. So in terms of the definition, this is how we can define them. So for the unsupervised learning algorithms, a data set contains many features, and then we learn useful properties of the structure of the data set. For example, anomaly detection is one where we may use an unsupervised learning algorithm. The algorithm looks at the data set and then learns a set of properties or the trends in the data, and then when it suddenly sees that the trend is violated, then it reports that as an anomaly. So it does not need any other knowledge except for the data that is provided to it. So effectively it learns the probability distribution Px by observing several examples of a random vector x, and then when it suddenly sees that the distribution has changed or there are values which do not fit the distribution, then it finds that as an anomaly. On the other hand, supervised learning algorithm has again a data set containing many features, but each example is also associated with a label or a target. So there is something that I am trying to learn. Maybe I am trying to learn the vector y, for example, and what I am given is for various values or various combinations of values for the random vector x, I am given the value y, and I am trying to estimate the probability of y given x, as opposed to learning just the probability of x in the unsupervised case. Now if we look at the unsupervised and supervised learning algorithms or the supervised learning methods, then though they seem fundamentally different, but the underlying problem is actually the same. It's only that we look at it from two different perspectives and therefore use different types of algorithms. So as you already know from the lectures on reasoning under uncertainty, the chain rule of probability defines the probability of x, where x is a vector having n different variables, n different random variables. The probability that x takes any value, a particular value, is given by the thing that you see on the right, namely I can use Bayes rule on this. Remember, this is the joint probability of those n variables. So this is actually my p of some of these n variables taking some values. So then that is given by I use Bayes rule repeatedly. So after using Bayes rule for the first time, I get this as P, let's say xn given x1 through xn minus 1 times probability of x1 xn minus 1. Right, so this is standard use of Bayes rule, and then I can recursively use the same thing on this, and then that will give me this expression. Now with this expression, what I essentially get is that the unsupervised learning problem, where I try to learn this is a set of supervised learning problems, because I can use supervised learning to learn the probability of xn given x1 through xn minus 1, then the probability of xn minus 1 given x1 through xn minus 2, and so on and so forth. So I can decompose the unsupervised learning problem into a set of supervised learning problems. And alternatively, I could also do the other way around, that is, I could solve the supervised learning problem, where we are interested in learning the probability of y given x, by using the traditional unsupervised learning technologies to learn the distribution pxy, and then inferring from pxy, from that distribution pxy, I can then infer this, and I can infer each of the terms in this, and thereby I can actually find this. So therefore, what it shows us that if you have an algorithm which can do unsupervised learning, then I can solve the supervised learning problem with that as well. So in a way, fundamentally, these are very closely related methods. But in the machine learning community, you will see there are algorithms which are specifically designed for supervised learning, and ones which are specifically designed for unsupervised learning. So why would one want to learn machine learning? So that's a very important question. The reason is that a static pre-programmed set of rules might give us very poor performance. That is, there are cases where we want to learn the behavior of the system without using pre-programmed rules, or by mimicking the behavior that we already know. As an example, you can think of an autonomous driving situation where I have to make a particular kind of turn in a road at a fairly high speed. So now if I design a set of rules or a set of algorithms which can negotiate this turn, it may not actually represent the very smooth way that a human driver will figure out how much of leeway to keep on either side of the road, and how it can negotiate this turn without too much of a jerk or too much of a wobbling around, etc. That kind of behavior may not be very easy to implement if I hard-coded the control completely. So that is why for this and many different classes of problems, people are contemplating of using machine learning, so that it kind of gives you a more human-like behavior in mimicking the way that a human actually performs the task, instead of defining the entire system with a set of maybe 400-500 variables and trying to model the behavior to perfection. The second problem is that for many complex systems, analytically specifying the system and analytically determining the control and the way that you want that system to function is very difficult to explain. Whereas you can always explain it in terms of examples, and examples may be abundant because of legacy data which is available, or you may be able to simulate the system and create a lot of data, but mathematically analyzing a system itself may be much more difficult. So that's where again machine learning is used. The third problem is the dimensionality of the problem can be very prohibitive. Typically we go for machine learning when you have a system where you have many variables, and but then all those variables may not be relevant for the task that you want to perform. So you need to eliminate a lot of variables, and it's not very easy to determine how to do that. And machine learning is one of the ways in which you may be able to reduce the dimensionality of the problem. You may focus on a set of significant variables and be able to produce almost perfect behavior using only that subset. And finally, in many cases it may be the only one tool which is the one to solve the problem at hand. Now while all this looks very rosy for machine learning, today we are in some ways facing the opposite problem, particularly with the new generation. I mean, I am sure many of you are also you may subscribe to that school, that you get any new problem, you simply use a set of machine learning techniques as black boxes. You try them out without actually understanding the structure of the problem, and many times when you do not use any domain knowledge or any understanding of the structure of the problem, you do not get the desired performance out of machine learning. Let us look at the problem of linear regression. So in linear regression, given a training data set which has m different data items, where each data item is a vector giving the values of the n different variables that we have, and the output is a linear function of the input which predicts the value of the scalar w such that the function y hat is some set of weights multiplied by x. So let me maybe take an example. Just hold on. Okay, so let me clear the canvas. There. So if I look at the n-dimensional space, so I have these n different dimensions. Let's say if n is 3, then I have these 3 different dimensions, and each data point here, obviously each data point here is a n-dimensional vector. So for example, if I say that this is, let's say, x of the first data point, x1, then I have a set of coordinates of this, that is x1, x2, x3, and this is for data point 1, this is data point 1, this is data point 1. Similarly, I may have another point here, which is this one, and that may be my data point 2, so x2, and then that is also three-dimensional vectors having the dimensions x1, x2, x3. So in terms of what you see there, the dimensions that I have here n is equal to 3, and the number of points that we have here, so I have 0.1, 0.2, 0.3, 0.4, so my m is 4. This is the number of data points that I have. And now what does linear regression try to do? It tries to find out a linear function over the n dimensions. So in this case it will try to find out y hat as some function over, let's say, w1 x1 plus w2 x2 plus w3 x3, which is what we are writing as the vec transpose times the vector x. Now essentially, in order to learn a function like this, what we need is to learn the values of these weights, the coefficients. This is linear regression. I can have polynomial regression. For example, I can have a quadratic regression where instead of just x1, x2, x3, I may have squares of those terms, etc. And essentially, based on the structure of the polynomial that I am trying to learn, the coefficients of the polynomial, in this case w1, w2, w3, are essentially the weights that I need to learn. So from the data, I will have to learn the values of these. Now, how do we go about doing that? So let us see. So the performance that we finally want to achieve is on the test data. Remember that there are two types of data that we talked about. That is, from the data which is available to you, you take maybe 80% for the training and you leave, let's say, 20% for testing the model after the training has been done. And obviously our goal is to ensure that the error that I see, or the mean square error that I see, in this case I am using the mean square error as the performance metric, that should be less. Now what is the mean square error for over the test data? So that is, as you can see here, that if there are m data points for the mean square this thing. So let's see, just give me a moment, let me put it back into full screen. Right. So this term is taking a data point and comparing the value of the function from the function that we have learned, that is this y hat, and then subtracting from there the actual value of y in the test. Now remember that the test data contains the value of y test. So that means I have the value of y test corresponding to all my variables that I have, namely my x1 through xn. Corresponding to that, I have the value of y test. So in the test data, I am given all these, and I am also given the value of the y test, and I have, let's say, m such data points. Then what do? I take the error for each of these data points. I see what the function is predicting and what is my given value of y test from here, and I take the difference between them and take the square of them, add them up and take their average. So that gives me the mean square error over the test. Now obviously at the training phase I cannot use the test data, because I have divided my data into two parts. One part will be used on training, the other part will be to use the model to test the model and determine how well it performs on the test data. So therefore what we want to do is to minimize the test error, but because at the training phase we are not allowed to use the test data, at the training phase we try to minimize the training error. So what is the training error? So just like you have the test error, the error over the test data, which is what you see here. Let me see here. This is the error over the test data. So you can have a similar formula for the training error. So instead of using the test here, for the training error you will use, instead of this test you will use y train, and you will use the y hat train and the y train here, and thereby you will compute the mean square error for the training. Now what we want to do is to choose the weights in such a way that this training error is the minimum. And for linear regression we can solve that problem by solving for this equation. That is, I want to find out the minima for the minimum, the mean square error for the training data. And by using linear algebra we can show that this reduces to this. That is, I can directly compute the values of the weights by computing this RHS, and this RHS can be derived out of the form that you see above. That is, from this form I can get this form, and this is possible because the function is linear. So I can use this matrix algebra to find out exactly the value of W. This is not possible in general for any type of regression function, but possible for linear regression. And we use the term linear regression also sometimes to refer to a slightly more sophisticated model called the affine model. And the only difference between the affine model and the linear model is that in the linear model you are only allowed to specify y as a function of x like this, but if you allow this plus b, then it becomes affine. So in terms of the of a graphical way of seeing this, this is what it means, that if you are looking at a linear regression, then suppose you have a set of points like this, then linear regression will have to use a line which passes through the origin, whereas you can use in affine models, you can use a function which is like this. This is also straight line, by the way, yes, but it does not have to start from x equal to rather y equal to 0. So at x equal to 0 y is b. So that is an affine model. So here you can see that linear regression finds out this blue line, and this line represents the function that it has learned, that is this one, and it minimizes the mean of the square of the errors, where these are my errors at the various different points, and if I square these errors and add them up, then this is the line which minimizes that error. And if you look at the plot of W1 versus the mean square error here, then this is the point where you get the minimum. So then that is the one. So here, for example, in this particular example, this W1 turns out to be 1.5. So then the function that we have learned is y is equal to 1.5x. Okay. Now, what do we do when it is not linear regression? We can still define the function in terms of these, the cost function in terms of these training errors and test errors. However, for finding out the point at which the training error is minimized, we will not be able to get a neat solution like you see here. Then what we resort to is that we can use things like gradient descent, or you can use things like simulated annealing to find out the minima of these types of functions. You had already studied this in a previous lecture. Now, a few important things that we need to understand while understanding machine learning in general are these terms of the capacity and the notion of overfitting and underfitting. So, the ability of a machine learning algorithm to perform well on previously unobserved inputs is called generalization. Now, let's understand what we mean by this. So, in machine learning, as I just now pointed out, there are a few things that we do. We first take the data, then we split that data up, maybe 80%, 20%, and say that this is my training data, this is my training data, and this is my test data. And then after I have done my training, then I test it with the test data, and if I am satisfied with this, then I take out this model and use it in the real environment. When I use it in the real environment, it is then subject to new data for which we did not have them in the training. So then that is where we are generalizing it, and we see that how well it generalizes. In fact, when we are testing the model using the test data, we are actually testing how well the model that you learned during training, when you did the training here, how well does it generalize to the test data. Okay. So we want to minimize the test error or the generalization error, but this depends on two things. One is that it depends on the accuracy of the model, that is number one, and the second thing is that it depends on the quality of the training data, that how well does the data represent the reality. Obviously, if the data is skewed, like you saw in the Simpson's paradox, or if you see that the data is inadequate, then obviously your learning will not be complete or will not be good enough. The other part is very important, that is, how do we accurately choose a model. So a model has something called a capacity. Now when we define a model, the capacity of a model is its ability to fit a family of functions. So for example, I may say that polynomials is one family, polynomials. So I may try to fit the data using a polynomial. The simplest polynomial is the linear function, which we saw just now, but I could look at a quadratic polynomial, a polynomial of degree 2, 3, 4, 5, etc., and then I can try to fit that function there. Now, that may be good for certain types of data, but for example, if you have a periodic data like a sine wave, then for a sine function, will a linear regression work well? No, because for a linear regression we'll have something like this as the fitting, and then there will be large amounts of error contributed by these parts. So a linear regression model cannot fit a sine function. Similarly, a polynomial will not be very good at fitting a periodic function like a sine, or maybe fitting an exponential function which grows very rapidly. So then you will not be able to fit it very nicely with a polynomial. If you use, but then the higher the capacity that you build, so the higher the complexity of the function that you allow, the more complex will be your learning task. For example, deep neural networks, they can model extremely complex functions, but because of that, our ability to learn them in terms of neural networks has problems because the model becomes extremely complex. The other problem that you have is that if the capacity of the model is very low, then you get underfitting. For example, if you try to take a sinusoidal wave and then you try to fit it with a linear function, or you take maybe even if you take, say for example, a quadratic function. If you take a quadratic function and then try to fit that with a linear function, then obviously that is not going to perform very well, because you will then have a lot of errors. So if you have if you choose a family which has a very low capacity, then you get what is called underfitting. And in underfitting, what will happen is that the model is unable to obtain a sufficiently low error in the training data. You will see in the training itself that it's not working very well. On the other hand, if you use a very high capacity, then we end up getting what is called overfitting. Overfitting is where the model now starts learning even the noise. Now remember that when I am presented with a data set may have a set of points which are accurate, but it may also have a few points which are essentially noise. Now a good fitting function will kind of fit it in a way that the noise does not affect you too much. But if you try to fit this using a polynomial of a much higher degree, then you may end up getting a function which overfits. So the next slide actually explains this. So here, as you can see, that we have a problem of underfitting in the first one, because the set of data points that you have here, I am trying to fit them using a linear function, and therefore I have a lot of error. These are all adding up as the errors, so there is a significant amount of error. If I choose a quadratic function, then you see we get a very good fit. But if I choose a function which is of even higher degree, like a polynomial of degree 9, a polynomial of degree 9 will also be able to fit this function exactly, fit this set of data points exactly, but then that is not really the function that fits this the best. It is actually now getting a lot of fictitious points like these points, which are not part of the function really. The function is like this. Now you may have some errors in this one as well, but these errors may not be so significant. Now if you want to fit them then you will now need a higher degree polynomial, and then that fitting may be something like this, which again is what is not desired. So when we talk about using a representational capacity or a capacity which is effective for the set of data points, then it may not be the one which fits the data the best, but it also fits it quite nicely, may not reducing the error to 0 but reducing the error to a substantially low value, but it is not unnecessarily enhancing the capacity of the model. So based on this understanding, there is a common knowledge in machine learning which is called Occam's razor. What it says is that among the competing hypotheses that explain known observations equally well, we should choose the simplest one. Now if you look at these three, they are all polynomials. This is a linear polynomial, the first one is a linear polynomial, this one. The second one is a quadratic function, the quadratic polynomial, and the third one is a polynomial of degree 9. Now among these, the linear function has high training error, that is, on the training data itself I have high error. In the quadratic function I have low training error. In the polynomial of degree 9 also I have low training error. But then Occam's razor tells us that between this and this, between the polynomial of degree 9 and the quadratic function, this one is the simpler of the two, so we should go ahead and use this. So this is a common sense reasoning to avoid the overfitting. So if you want to build this into something like a theory, then this is what we mean. So on the x-axis I have the capacity. So on the x-axis I have capacity. So as we go in this direction, the capacity of the model increases, which means that I am choosing more and more complex models. And on the y-axis I have error. So now as you can see, I am looking at two things. I am training with the training error. Then when I am done with the training, then I use that on the generalization data, that is on the test data, and I compute the generalization error. Remember that I am always, during learning, I am targeting this one to reduce training error, with the intention that I will have lower generalization error, but at the time of training I do not know the generalization error because I will use it in the next step. So if you look at the training error, then you see that the training error, as I increase the capacity, so initially the training error was high, that is here the training error was high, it was something like this. Then as I increased my capacity, my training error started falling. So here the training error is even lesser, and then this way I continue, and at some point of time the training error seems to reach a kind of valley, and thereafter there is not any significant dip in the training error, though as you can see that over a period of time the training error actually dips further. And now the point is, where shall we stop? So by using Occam's razor, we say that, well, in these points the rate of decline or the gain that you get by increasing the capacity is not so significant, so we choose this as the optimal capacity. So we choose this as the optimal capacity and say that this is the capacity of my model. Now in the case of polynomials, for example, this could be degree 1, this could be degree say 2, and so forth, and here I get maybe degree 5, and then I say that, well, I am only going to choose a polynomial of degree 5 for this particular data, and then this is my the training error that I get. Now when you apply that on the generalization on the test data, then you see that this is the error that you get. Now let's understand a few things. Why is the training error still dipping as we increase the capacity? Now you see that the data has some amount of noise. Now in the optimal capacity, if we stop there, then we kind of accept the deviations that we still have. So maybe you have got a function which fits the points, almost all the points very well, and there are a few points which are not exactly on the function that you have. That's why we have some error. Now if you increase the capacity, then something like this is going to happen, that you will now start fitting more number of points, and then if you fit more number of points, you are actually now fitting the noise. So by increasing the capacity, you are not making the model any better, but you are bringing in additional fictitious complexity into the model, thereby reducing the error on the training data. But when you take it to the test data, you will see that its performance will start becoming worse. So the second thing that we need to understand here is that when I choose this optimal capacity, my generalization error is here, but then if I increase the capacity even further, then my training error goes down, but my generalization error goes up. Why does that happen? It happens because when I go to this capacity, then I have actually chosen a function which kind of manages to fit all the points no matter how. Now that is good for this data, but when you present new data, then maybe this was actually a function like this, and then when you present the new data, maybe in the new data you have a point here, but then for that point I now have a significant error, that is this much of error. So the generalization error goes up, and this is called the generalization gap. Why do we have a gap between the generalization error and the training error for even the model with the optimal capacity? Now that is again true because you see, all we are doing in learning is trying to find a function which mimics the behavior of the actual function. What the actual function is and the function from which the data is getting generated, we do not know that. And that function may be a very complex function having many more variables, and we are trying to use machine learning so that we don't have to deal with so many variables. So we are trying to learn or fit the behavior in terms of a simpler function. But that simpler function, while it fits the training data really well, will still produce some error when I am presenting it with new points. So that's why I will have some amount of generalization error which is more than the training error when I use it on the test data. And there is a very nice theorem which says that there is no free lunch as far as machine learning is concerned. Now what does the no free lunch theorem tells us is that, well, you have learned some function. So I do not know what is the real function, but what I do know is that based on the data that I have learned some function, maybe something like this. Now that kind of fits the set of values that I have learned. So let me draw the points on the basis of which I learned this. Maybe the points on the basis of which I learned this are these. Maybe I have a point here, point here, point here, maybe a point here, maybe a point here, etc. Now what the no free lunch theorem says is that I can never know what the actual function is. I just have these set of, let's say, 5 blue data points. And I have found out that this function, which I chose based on my understanding of the capacity, this fit it pretty well. Now, if the data that was given to me was kind of skewed and not representative of the actual distribution, then there can be potentially another data generating distribution which produces these blue points and also produces some points like this. Now these points, these new points, let me kind of draw them by circles so that you can distinguish them between those and the ones that we had here. Maybe we have one here as well, and let's say this is a new one. Now if these points were not there in the original data, but then they show up later, then we realize that, well, this is not a good fit anymore, because I did not know that such points could exist. So therefore I found that previous function, the red one, to be fitting it quite nicely. But now with this new information, maybe something like this would be a better fit. Now you see, there is no end to it. Now if you think that this is a good fit, and then let's say you are exposed to some new data, maybe one which has here, one data here, one data here, now you know that, well, this is also not good. So what the no freelance theorem effectively says is that for any set of data that you have, if you have a machine learning algorithm which fits that data very well, I can always have a different data generating distribution where the error is arbitrarily high for the function that you have learned. So what it essentially tells us, that in the absence of any domain knowledge, in the absence of any constraints or anything that you know about the distribution from which the data is coming, there is no machine learning algorithm which is universally superior to any others. They can all suffer from the same amount of error by changing the data generating distribution. So therefore it is important that if we have domain knowledge about the distribution from which the data is coming, then we will choose the function by which we try to fit that data with that understanding of the underlying data distribution. Now, how do we go about choosing this capacity is another very interesting problem. So if you look at this data, so there is a, let's see what are the components of this. So I choose a set of things here. Give me a moment. Yeah, I have a this blue refers to the training with a quadratic function. So as you can see here, in the training with the quadratic function, the training starts where? Here, and then it moves on like this and then settles down into some amount of error. So the training data does not really reach zero training error. So there is always this amount of training error. The training error here, as you can see by the settling of the blue line, the training error is something like this much, right? Now if you look at the performance of this quadratic function on the test data, then you see that for the test data it comes down like this with the increasing number of training samples. As you train it with more and more samples, it comes down, and then it settles somewhere around this level. So if you look at that level here, then we get something like this where the green curve settles. So this is my generalization error. The generalization error is the gap between the generalization gap, as we saw in this. The generalization gap is the gap between the curve for the training error and the curve for the generalization error. So there you see that this is the gap that you see here. Now this gap is because the quadratic function is not optimally fitting. It's not the optimal capacity one. On the other hand, if you look at the optimal capacity, I mean, we don't know that a priori, of course, but suppose we know that the distribution from which the data is generated. So if that is the capacity, if I know the capacity of the data generating distribution, and then I use that for training, then you see the training error initially with the few samples, it goes up like this and then comes and settles down absolutely, very near zero. There is still a very small error which is due to the noise, but it is almost at zero. You can see the green line just sitting up atop the x-axis. And then when you use this, let's see what happens to the test error. Now the test error actually drops down much below the green one. So you see that with the optimal capacity, now the test error is much better. So you have a lesser generalization error when you use it on the test data. Now the way to choose the optimal capacity, as we also saw in the figure that I used earlier, that you keep on increasing the number of training examples. So if I look at, say, let's say 10 training examples, so that then I am here with 10 training examples, there I find that the optimal capacity is 6, maybe something like this, 6 here. What does that mean? So when I train it up to this point, up to 10 examples, what I do then is I see what is my training error if I change the capacity, or maybe in this case the capacity could be the degree of the polynomial which I am trying to fit, from a set of values. Maybe I try out 5, I try out 6, and I try out 7 and 8. Now out of these I find that the error is minimized in the capacity of 6. Now do I stop there? No, I keep on increasing the number of training examples. Now when I increase the number of training examples to, let's say, 100, then I find that now the optimal capacity is close to 10, and in this way it keeps on climbing. After a period of, after adding a certain number of examples, what we see is that regardless of how many more examples you add, the capacity at which I get the optimal error or the minimum training error settles down to some value. So here it's settling down to something around 15, 16. So around that value it is settling down. So then we know that the best capacity for this is the family of polynomials of degree 15 or 16. So that means that I choose the skeleton now. Now I choose the skeleton where I have a polynomials, this family of polynomials of degree, let's say 16. So that is my family. And now for this family, I need to learn the weights or the coefficients of the polynomial such that it fits the training data the best. So that is the way that we choose the capacity and then go ahead and do the regression to find out the values of the weights for that. Now as you saw, that something like choosing the degree of the polynomial is what we may say is a hyperparameter of a machine learning algorithm. So typically a machine learning algorithm may have many different hyperparameters. For example, in neural networks, the number of layers may be a hyperparameter. the connectivity between the different layers may be a hyperparameter. So I choose these hyperparameters. We shall see many of these as we go along. In the case of regression, as we saw in this lecture, the hyperparameter could be the degree. So I need to choose the hyperparameter, and then I need to choose the exact parameters or the weights, if you may say so, for actually learning the function in the family that is defined by the hyperparameters. So to do this check, or to find out that what is the optimal hyperparameter value, in this case let's say the degree of the polynomial, what we do is we again split the training data into two parts. Remember that the entire data was originally split into the training data and the test data. Now the training data is again split maybe let's say again 80-20 into the part that we use for learning hyperparameters and the remaining part which we use for training the model after we have chosen the hyperparameter, or after we have trained it and then checked out with the hyperparameter values how well it is performing. So for example, here we ran the training each time and then verified the model with respect to the hyperparameter values for each hyperparameter choice. Then we see how well it is performing with that number of training examples, and we progressively increase the number of training examples and then finally choose the value of the hyperparameter. And then once we have chosen the hyperparameter and then trained the model with respect to the training data, then the data is ready, and the model is ready rather, and then I can use the model to do actual predictions or actual decision making process for which we build the model. So this summarizes the machine learning process. So we start with a system having many different variables. The process of feature extraction reduces the number of variables to the set that we need. Then in parallel what we do is we use the training and the validation sets to choose the parameters and then run the training to learn the set of coefficients or the set of weights in my learning function. And then once I have done that, now the machine learning part has been completed, and now I can use the model for doing predictions or classifications or whatever I have actually designed it to do. So this, in the summary of the steps, we do the selection of an algorithm, and we do feature selection, then we do the training or the model building. There is also a step called cross validation, or when we try to optimize the parameters, and then we do the test, and then we are ready to apply the model. So this is the general overview of what machine learning is about. What we intend to do from here on is to dive into different types of machine learning problems, and accordingly we will learn how to look at these things that we have learned today, like overfitting, the noises, the different types of methods that we use for classification, for regression, etc., etc., and how to bring all this together. And then finally we are also going to discuss how to integrate the classical AI in terms of planning, deduction, heuristic search into the framework of machine learning. So thank you very much for your attention and have a good day.